The rain begins in October and does not stop until April. 6 months of water falling from low clouds that never break. The forest floor never dries. Moss grows on moss. Wood left on the ground dissolves into the earth within a season. Everything exposed to the air turns slick with moisture, then soft, then gone. Yet here, in this drowned landscape stretched along the Pacific coast, from Alaska to Northern California, indigenous peoples built structures that stood for generations. Not temporary shelters, not crude lean-tos patched together from bark and branch. These were buildings among the largest in pre-contact North America, some measuring 40 feet wide and over 100 feet long. Houses that held extended families of 50 people or more. Houses filled with tons of dried salmon, carved cedar boxes, ceremonial regalia, tools, and wealth accumulated over lifetimes. Houses that could not afford to fail, because everything inside them would rot within days if water found its way in. The question was never whether the rain would come. The rain always came. The question was how to build something permanent when the environment destroyed permanence as its fundamental operating principle. And the answer lay in a single tree. The Kwakwaka'wakwa called it the tree of life. Western red cedar grew straight and tall in the coastal forests, some specimens reaching 200 feet with trunks 10 feet across. But size alone did not make it valuable. Cedar possessed a property that transformed the calculus of survival in a saturated world. The wood itself resisted rot. The resistance came from chemistry, not structure. Cedar wood is saturated with natural essential oils, aromatic compounds the tree produces as a defense mechanism. These oils repel the organisms that thrive in constant moisture, the fungi that break down cellulose, the bacteria that colonize damp surfaces, the insects that burrow into softened wood. A plank of cedar exposed to rain does not decay the way other woods do. It weathers, it grays, but it holds its integrity for decades, sometimes centuries, while the forest floor churns through everything else in years. This passive biological defense meant that a house built from cedar required far less maintenance than any alternative. There was no need for constant replacement of rotted boards, no annual recoating with preservatives that did not exist. The material defended itself, year after year, against the very conditions that defined the climate. But having rot-resistant wood solved only the first problem. The second was obtaining it in the quantities required for monumental architecture without the use of metal tools. Cedar's grain structure made this possible. Unlike many hardwoods, which grow with twisted grain patterns and dense knots, cedar grows remarkably straight, with minimal branching low on the trunk. This means the wood can be split along its grain rather than cut across it. Splitting requires force and precision, but not the continuous abrasive cutting action of a saw. It works with the wood's internal structure rather than against it. The technique was exact. Craftsmen used wedges carved from yew wood, a dense, fine-grained species that could take repeated impacts without fracturing. The wedges were often hardened by scorching their surfaces over fire, creating a tougher outer layer. To cushion the blows and prevent the wedge from splitting under impact, twisted cedar bark was bound to the top. The striking tool was a maul made from stone or carved from antler. A harvester would select a section of the trunk, then drive the first wedge into the end grain, starting a fracture. Additional wedges were inserted along the propagating split, each blow forcing the crack to travel deeper into the wood. If done correctly, the fracture followed the grain perfectly, separating a plank 4 to 6 inches thick and as long as the log itself. The cut ends were finished with an adze, a hand tool with a curved blade that could smooth the surface and remove rough edges. This method allowed the extraction of massive planks from a log, or even from a living tree. Some harvesters practiced live planking, removing only a vertical section of the trunk while leaving the tree standing. The tree would continue to grow, its cambium layer slowly healing the wound. These scarred specimens, called culturally modified trees, still stand in Pacific Northwest forests today. Silent markers of a harvesting tradition that operated within the regenerative capacity of the forest, rather than beyond it. The spiritual framework reinforced this restraint. Before taking any part of a cedar, the harvester offered a prayer of respect and gratitude. This was not decorative ritual. It was understood that improper harvesting, cutting without acknowledgement, would bring a curse from the other cedar trees in the forest. The belief system encoded a conservation ethic into the act itself, ensuring that the resource enabling survival would remain available to future generations. The result was a sustainable timber economy operating at a scale that would have required industrial sawmills in other contexts. Archaeological evidence from sites like the Meyer House near Portland, Oregon, shows structures that consumed several 100,000 board feet of lumber over their operational lifetimes. This was a monumental construction achieved through knowledge of material properties rather than advancement in tool technology. With the planks ready, the question became how to assemble them into a structure that would keep the interior dry under months of unrelenting rain. The house frame was post and beam, massive cedar logs set vertically into the ground or onto foundation stones, with horizontal beams spanning between them. This skeleton bore the weight of the entire structure and remained in place permanently, even when the house was dismantled seasonally. The walls and roof were constructed from thick planks, each one carefully positioned to create a continuous barrier against water intrusion. The roof design was critical. Northern groups like the Haida and Tlingit favored gabled roofs with two angled planes meeting at a central ridge. In the Salish Sea region, low-slope shed roofs were more common, typically slanting from front to back. Both designs shared the same principle: ensure rapid runoff. Water that sits on a surface finds its way through seams. Water that flows off immediately cannot penetrate. The planks were laid in overlapping courses, each row positioned so that water running down one plank would flow onto the surface of the plank below, rather than into the gap between them. This staggered arrangement created a shingled effect, multiplying the thickness of the barrier. Even if moisture seeped past the first layer, it encountered a second, then a third, each overlap shedding water downward and outward. At the apex of the roof was the smoke hole, a deliberately open section that served two functions. It vented smoke from the central fire pits that burned continuously inside the house, preventing the interior from becoming unbreathable. But it also managed humidity. In a saturated climate, moisture accumulates inside any enclosed space from respiration, cooking, drying clothes, and the sheer presence of bodies. Without ventilation, this internal humidity condenses on cold surfaces, promoting mold growth and wood decay from within. The smoke hole allowed humid air to escape, maintaining a drier interior environment even as rain fell outside. But the roof only managed water from above. The more insidious threat came from below. Coastal soil in the Pacific Northwest remains saturated for much of the year. Groundwater sits just inches beneath the surface. Rainwater that falls onto the ground does not drain quickly. It pools, seeps, and rises. Any structure built directly on this saturated earth would absorb moisture through its base, wicking water upward into the walls and floor. Within weeks, the lower portions of the house would begin to rot regardless of the rot resistance of the cedar. The solution to this was elevation. The heavy post and beam frame was set on pilings or foundation posts that lifted the main floor several feet above ground level. This physical separation created an air gap that broke the moisture transfer path. Water could pool beneath the house, but it could not reach the living surface. Rain splashing off the ground could not contact the structure's base. The elevation also improved ventilation, allowing air to circulate beneath the floor and evaporate any moisture that did accumulate. Among the Tlingit, the space beneath the elevated floor was used for storage, an efficient use of volume that would otherwise serve no purpose. In some high-ranking Haida and Tsimshian houses, the main floor plane stepped downward toward the central fire pit, creating a sunken hearth area. The surrounding elevated floor retained heat radiating from the fire while keeping sleeping and working surfaces dry and clean, physically separating different functional zones within the house. Elevation addressed moisture rising from the ground, but water also moved horizontally across the landscape, flowing downhill during storms and pooling wherever topography created low points. A house positioned in the path of runoff could find its foundations undermined by erosion or its perimeter saturated to the point of structural instability. This required civil engineering at the site level, not just architectural design at the building level. Archaeological excavations at coastal village sites have revealed sophisticated external drainage systems. At Ozette, a Makah winter village on the Olympic Peninsula, and at Tokwat sites on Vancouver Island, researchers uncovered deliberate stormwater management infrastructure designed to protect the houses from hydrological threats. The most striking example involved whalebone. When a whale washed ashore or was successfully hunted, every part of the animal was utilized. The scapulae, shoulder blades, are large curved bones with a naturally robust structure. These were placed edge down into the sandy coastal soil, positioned in line to form continuous channels. Storm water flowing down from higher ground would be captured by these channels and directed toward the beach, away from the house foundations. This was not a trivial engineering decision. Simple trenches dug into sandy soil collapse and fill with sediment within a season or two, requiring constant maintenance. Whalebone, by contrast, is dense, durable, and retains its shape under the pressure of flowing water and shifting soil. The bones created stable, long-lasting drainage corridors that required no annual re-excavation. It was infrastructure built from biological materials because those materials outperformed any alternative available in the pre-industrial toolkit. Further evidence from Ozette House 2 revealed subfloor drainage channels engineered to intercept water seeping from a nearby hillside. The channels redirected this flow away from the house interior, preventing saturation of the floor supports. Additionally, built-up ridges of shell midden, accumulated refuse from generations of shellfish consumption, were positioned around building perimeters to intercept roof runoff. The midden acted as a permeable barrier, absorbing water and preventing it from pooling directly against the house base, while simultaneously stabilizing the surrounding ground. These measures demonstrated a comprehensive understanding of site hydrology, where water would flow during heavy rain, where it would accumulate, and how to redirect it before it became a threat. Yet even with a dry structure, survival depended on keeping other things dry, specifically food and tools. The abundance of the Pacific Northwest was seasonal and concentrated. Salmon runs occurred in predictable pulses, bringing massive quantities of fish upriver in a matter of weeks. During these runs, communities harvested far more than they could consume immediately. The surplus was smoked or dried, then stored for the long months when fresh protein was scarce. A single household might store hundreds of pounds of preserved salmon, along with dried berries, roots, and rendered oils. This food had to remain dry, because moisture leads to mold. Mold renders food inedible, and in a pre-refrigeration context, there was no second chance. If the winter stores spoiled, the household faced starvation. However, the storage solution was vertical. Under the rafters, high above the floor, open shelves and platforms were constructed. Dried fish, sealed cedar boxes, woven baskets of berries, all were placed on these elevated platforms, maximizing distance from ground moisture and minimizing exposure to pests like rodents that could not easily climb to the ceiling. Positioning storage near the smoke hole provided an additional benefit. Smoke from the central fire rose continuously, bathing the stored food in preservative compounds. The smoke deterred insects and inhibited microbial growth, adding a secondary layer of protection beyond simple elevation. The food was simultaneously kept dry, kept away from pests, and actively preserved by the ambient environment of the house itself. Sleeping platforms followed the same logic. Bunks were built above the main floor, elevating sleepers away from cold air that settled at ground level. and away from any moisture that might seep through despite the elevated foundation. The house operated on a consistent internal rule. Everything critical to survival goes up. But the plank house itself, for all its permanence, was not entirely immobile. For groups in the Salish Sea, the seasonal cycle of resource gathering required movement. In spring, as salmon began their runs and shellfish beds became accessible, families relocated from winter villages to temporary fishing and gathering sites closer to the resource zones. Remaining in the winter village year-round was inefficient. The distance to productive areas was too great for daily travel. The challenge was constructing shelter at these temporary sites without repeating the immense labor of building a full house from scratch. The solution lay in modular construction. The heavy post and beam frames were left standing at the permanent winter village. The thick cedar planks that formed the walls and roof, however, were transportable. In early spring, these planks were removed, carried to canoes, and transported via water to the summer sites where lighter frames awaited them. The planks were reinstalled, creating a full-sized house in a fraction of the time it would take to process new timber. This system was only feasible because of the advanced naval engineering of the Pacific Northwest. The canoes used by these groups were among the largest and most sophisticated in North America, carved from single cedar logs and capable of carrying tons of cargo in open ocean conditions. The plank house and the ocean-going canoe were co-evolved technologies, each enabling the other. Without the canoes, the planks could not be moved efficiently. Without the planks, the canoes would have no cargo valuable enough to justify their construction. When autumn arrived, the process reversed. The planks were disassembled, returned to the winter village, and reinstalled on the permanent frames. The house, which had been scattered across multiple locations, reconstituted itself, ready to provide shelter through the months of rain. This modularity reflected a broader philosophy. Permanence and mobility were not opposites, but complementary strategies. The frame represented a multi-generational investment and a sense of territorial stability. The planks represented seasonal flexibility and efficient use of labor. Together, they created an architectural system that was both monumental and adaptive. Yet the house was never understood as merely a functional object. It was a container of identity, history, and spiritual power. And the plank house succeeded not by resisting water, but by controlling it. The cedar oils created a passive chemical shield against biological decay. The angled roof directed high-volume rainfall away from the structure. The elevated foundation separated the living plane from rising ground moisture. The external drainage infrastructure managed site-level runoff before it could threaten the building's base. Inside, vertical storage kept food and tools away from dampness, while smoke from the central fire added a secondary preservation effect. Each layer of defense addressed a different scale of the water problem, from the molecular interactions of wood oils repelling fungi to the civil engineering of whalebone channels redirecting stormwater. The system worked because it acknowledged the inevitability of the rain and was designed for management rather than evasion. The houses stood for generations. Some frames remained in use for over a century, supporting successive installations of wall planks as the older ones weathered and were replaced. The continuity of the structure mirrored the continuity of the families who inhabited them. Multi-generational units that accumulated wealth, knowledge, and social power within the same physical space where their ancestors had lived. When European explorers arrived in the 18th century, they encountered villages of houses larger than most buildings in their own countries, constructed without metal, organized around principles of hydrological control they did not immediately recognize. The explorers saw primitives living in wooden huts. They missed the engineering. The plank house tradition declined in the late 19th and early 20th centuries as forced assimilation policies, disease, and economic disruption shattered indigenous communities across the Pacific Northwest. Many of the great houses were abandoned or dismantled. The knowledge required to split cedar with wedges, to position planks for optimal runoff, and to site a house within the watershed's flow was partially lost as the social structures that transmitted it collapsed. But the trees still stand. The culturally modified trees, scarred by live planking centuries ago, continue to grow in coastal forests. The archaeological sites, buried under centuries of midden and soil, preserve the whalebone drains and subfloor channels. The houses that remain or have been reconstructed still demonstrate what is possible when architecture is designed not to dominate an environment, but to exist within it. The lesson is not that cedar is a miracle material, or that pre-industrial peoples possessed some lost wisdom inaccessible to modernity. The lesson is that survival in challenging environments requires precise attention to the mechanisms of threat. Water does not care about human intention. It will find every gap, exploit every weakness, and accumulate wherever gravity and permeability allow. The only defense is to understand where the water will go before it gets there, and to design every element of the structure to redirect, deflect, or absorb it. The plank house was not built to escape the rain. It was built to live with the rain, year after year, generation after generation, in a landscape where the water never stopped falling and never would. That is the achievement. Not defiance, but accommodation. Not resistance, but control. A house made from the rhythm of the rain itself.